So continuing from what we were looking at on the previous video to this one, we were looking at how you could display on an argand graph or diagram a rectangle or the polar form. There was two forms. This one's the rectangle and this one's the polar. If I get the modulus of this, and this is called the argument, the angle. Okay, so the point of this video is to see how we convert from one to another, doing it mathematically. Now there's an easier way. There's several easier ways actually with software. One of the easy ways to hand is to use a calculator. A lot of calculators do the conversion quite easily. But quite often in assignment questions you have to, or exams, you have to display it in a mathematical method. And it is actually very easy. All we do really is we treat it as a triangle. Okay, so it's a triangle. How do we find the long side of a triangle? Easy, Pythagoras. So Z is going to simply be the modulus of Z. Remember, we call the modulus the length of the line. Modulus meaning it's positive. It's not going to, you can't have a minus line in a triangle, so it's going to be positive. So it's simply Pythagoras. So it's simply going to be the square root of 3 plus the square root of 4, which will give me square root of 25, which gives me 5. And probably most of you will recognise it's a 3, 4, 5 triangle in effect. 3 along here, 4 up there. Okay, so that gives me the modulus. How do I find the angle? It's so simple. SOHCAHTOA, as you probably know it as, SOHCAHTOA. So we're going to use, we've got the opposite and we've got the adjacent to the angle. So the best one is to use tan. We could actually use, now that we know the length of this side, we could use any of them, cosine or sine, but it's always best to use your starting point in case you've got any errors in this. I mean, this is a nice round number, whole number, but imagine it if it was square root of 2, for example. There'd be a lot, or anything where you've just got decimal points that continue and you end up having rounding errors. So the best thing to do is to use these two lengths, your starting points. Even if these are decimal points, at least you're reducing your errors, number of errors. So it's simply going to be tan, and we're looking for the angle, not the ratio of the sides. So it's going to be the inverse of tan. So it's going to be the inverse of tan of the opposite, which is 4 over 3. Simple as that. Put that in your calculator and you get 53.13 degrees to 2 decimal places. So the way to write it for the imaginary, for the polar method, is 5, and then we use this symbol. It's a bit like an L that's collapsing, and a bit like a triangle. And then the angle, which is 53 degrees, 0.13. So it's easy. Easy enough that. Let's have a look at another example. Let's say we've got a minus 1, 2, 3, 4. So minus 4 there. Okay. So this time let's look for Z equals 3 minus J4. So that one's going to be down here. So let's see if I can join that neatly, nearly. So the Z of that one, it's the same principle. Treat it like a triangle. So same mass for the length will give me 5. When I do the angle, I'm going to get the same answer. 53 degrees, 53.13 degrees. But remember what I said on the last video, these directions are all positive and this direction is negative. And you can actually go all the way around if you wish, but there's no real point. So it's going to be minus 53, because it's 53.13 again, but it's in the minus direction. So this time we're going to get minus 53.13. Now when you put this in your calculator, you're doing this in your calculator, if you put a minus 4 in there, like thus, you would get a minus result, so it'd give you the answer straight off. If you think about it though, and it's why it's a good idea to do little sketches, just to get a mental image of where it is. You don't actually need to bother putting the minus sign in. It's up to you, whichever you find easiest. So in this example, let me just remove that minus sign from there, because it doesn't apply to that. But in this example, you'd put a -4 then if you prefer. But myself, I never bothered, I just know it's a minus. If we look in the other segments, over here, we did see this in the last video. So if we had one over here, like that, then that one, that angle, it's that angle there that we want. Okay, so we would treat this as a triangle and we would get this angle there, but we actually want this one. So that would be 53.13, so we'd have to remove that from 180. Now if you do it in your calculator, that's not, if you use one of the calculators that allow you to convert between the two, it'll just do that for you anyway. Or software, any software that you may use. I often talk about Wolfram Alpha online that's free. That would do it for you anyway as well. That would do a conversion and plot it on a little graph for you and everything. Okay, what happens if I go the other way? If I'm not given this, but I'm given this or this, what would I do? Well, it's straightforward. It's SOHCAHTOA. So I know the angle and I know that length. I know the hypotenuse. So I'm going to use, so to find this one, I would be looking for, which is the imaginary bit, I would be using sine. So that would be, let's do that one. Let me just lose that for now. Okay. So I would be using, and this is my information, this is what I'm working with. So I know it's 5. So SOHCAHTOA would say that sine theta would equal the opposite of the hypotenuse. Now I know the hypotenuse because it's 5. So in other words, I've got sine theta, and theta is 53.13 would equal the opposite, which is what I'm looking for, divided by the hypotenuse. So rearrange that, bring the hypotenuse, multiply through by hypotenuse, however you want to look at it. Hypotenuse is 5, so I've got 5 sine 53.13 would equal the opposite, which would be 4. You might get something like 3.999 or something, depending on your errors, because this is not bang on precise, but it should be 4. Then if I do the other one, if I'm looking for the real part, then I'm going to use cosine. So it's going to be 5. If I do the same process, I'll get 5 cosine 53.13 would equal the adjacent, which would give me 3. Okay, so the formula is always the same. The modulus always comes to the front as a multiplier. So these formulas are always the same. So your modulus times the sine will give you that should be a j term. So let's put that in, or an imaginary term. And this would give you the real part. So it's always the same. In fact, there's a way of writing complex numbers using those two forms where we have a j for the sine. Okay, so let's have a quick look at another example. Let's say this one, more trickier. The easiest way is just to treat it as a triangle again. Okay, that's where doing a little sketch comes in great. And so the easiest way is to use this inner triangle, not this one. It takes more work to do that. So use the inner triangle of 53.13. You're doing exactly the same maths, but the difference is you'd have to know, a little sketch would tell you that this is -3 to here. So the real part is -3 and the imaginary is minus j4 from the same results. So that's why doing a little sketch is a great idea to figure out what's going on. You can do it purely in maths, but it's with the angles, and it will work. But I think it's a lot easier just to do a little sketch and work with your treat your triangle, treat it as a triangle. This is a triangle like that. Okay, and you've got that angle there, and you've got that length there of your hypotenuse. So from that you can find the other two sides. So that's a triangle like that. This is obviously a triangle like this. Okay, if I had one in this segment, it would be that way. You'd have 5 there, and that would be your 3 and your 4, which would be minus, plus and minus like that. Okay, so I hope that makes sense.